Yeah, a little review of our.
Can I shut the door?
Yes, Lewis dot. So, octet rule. Yes?
Can I go to the office? I had to send something in the morning. I forgot.
Unlock the door. You just twist it and then twist the handle. All atoms want 8 electrons around it. So make sure after drawing the Lewis dot structure, or Lewis structure is probably more accurate, that every atom satisfies the octet rule. Exceptions that they must also satisfy: hydrogen and helium only need 2 to be full. Beryllium only needs 4 to be full. Aluminum and boron only needs 6 to be full. Elements and period 3 are greater may have more than 8. This one I'm not going to really do too much other than this one, SF6. Obviously, you have to connect all the fluorines together. There's no way around it, giving us a total of 12 around the sulfur. But you should know that each fluorine needs 8 around it. So 1, 2, so 3, 4, 5, 6, 7, 8, all around them. So there should be 8 around these. Again, I'm not going to give you any real major exceptions like this. But you should, so because sulfur is in period 3, it's allowed, so they are allowed more. Normally they don't have more, but they are allowed in these specific circumstances to have more. So that's the octet rule. The least electronegative element is usually the central atom. Most of the time, it's the single element. Atoms of higher En usually go on the outside. Most of the time, there are multiple elements. Exceptions. Hydrogen always goes on outside. Carbon always goes in the center. No unpaired electrons on Lewis structure. Shared pairs are represented with a line. So, in other words, a line represents a pair of electrons. A shared pair. So a line is equal to 2 electrons. One little helpful advice that a lot of people seem to be getting wrong whenever they come show me what they made. Count the total number of available electrons. You obviously will have exactly that many electrons at the end. On Lewis structure. For example, oxygen has 6 valence. This hydrogen and this hydrogen both have 1 each. So a total of 8 valence available. And when we draw the Lewis structure, you should be able to count 8 in her. So a line represents 2 electrons. So counting them. So this is 2, 4, 6, 8. So what you should do is when you're done with your Lewis dot, count your total electrons and make sure that you have that you've used them all and you haven't added any extra ones or left them off. Also check and make sure that all the valence all the octet rules are satisfied. Hydrogen only needs 2. It has 2, so it's good. Hydrogen has 2, and oxygen has 8. You didn't add any. There's no 9 around here. And you didn't forget to add some. And the last thing I'll add for ions, put bracket around structure with charge on outside. It was yesterday, right, that I looked at made y'all do sulfate and figured out that I forgot about a rule. I post some videos on it. I'm not going to give you any of that, as I don't teach formal charge. I should, but this unit's already too big. There's a lot of information that you have to memorize.
Hi, this is Dr. B. Let's do the SO4 2- Lewis structure for the sulfate ion. On the periodic table, sulfur 6 valence electrons. Oxygen also has 6. We have 4 oxygens multiplied by 4, and these 2 valence electrons up here, we need to add those as well. That gives us a total of 32 valence electrons. We'll put the sulfur in the center, and then the 4 oxygens will go on the outside. Next, we'll draw bonds between the sulfur and the oxygens. So there we have 4 bonds, and we've used 8 valence electrons. Just go around the outer atoms and make sure they have octets. So we've used 8, 10, 12, and 32. Looking at
So what he just did is another way you could do this. So we know sulfur is going to go in the middle. We know oxygen is going to go outside. We know that they're going to have single bonds here. And we need a total of 32 electrons. What you can do is try satisfying the outside first, like he did. And then afterward, go through and check all the octet rule. So here is 8. That has 8, 8, 8. Sulfur has 8. Octet rule is done. It's all satisfied. You're mostly done. There is something I don't teach, and you guys don't have to worry about. It's about formal charge. Formal charge is a theory that states that after we get a possible configuration, we want to choose a setup such that the lowest, we have the lowest number of formal charges. We want formal charge to be as close to 0 as possible. Things do not like to have a charge.
2, 4, 6, 8. But we're not quite done yet. Sulfur is in the 3rd period of the periodic table.
So it has the octet exception that it can hold more than 8.
That means it can hold more than 8 valence electrons. So we really do need to check our formal charges. So to calculate the formal charge on the sulfur, we see that...
And this is the equation for formal charge. Total number of starting valence electrons minus any non-bonded or lone pairs. And then how many bonds in total. You take the bonded, a line, which is 2, divide it by 2, and that tells you how many bonds it has. This is the formal equation. These are all identical. So we have 6 on the oxygen, minus 6 non-bonding, so that's 0. And then we have 1 bond, so we subtract that. This has a formal charge of -1. This has no lone pairs. And it started with 6, so 6 minus 0, and it has 8 electrons around it. Take 8, divide by 2, that gives you 4 bonds. This has a formal charge of +2. We can make this closer to 0 by moving some of the electrons to sulfur, decreasing the formal charge. What is the smallest? So these formal charges, so this is -1, -2, -3, -4. If you add up all these together, you get -4. +2 gives us a total formal charge of -2 for the ion. the ion is going to have a charge of -2. What is some way we can, just thinking about it, what is the way we can get all the formal charges as close to 0 as possible, but still have them add up to -2? Well, if we can somehow get all of these having 0 charge, except for 2 of them possibly having a charge of -1, that's the closest we can ever get to being all 0, right? This is obviously 2, so that's not as close to 0 as possible. We can get a charge of -1. -1 or +1 is closer to 0. So we can envision that we can get three of these as 0 and 2 of them as -1, and that will give us closer formal charge to being all 0.
Sulfur on the periodic table, group 6 involved in bonds. So that's 2 formal charge for the sulfur. For the oxygen, it's also in group 6 or 16, so it has 6 valence electrons. Up here, non-bonding, we have 6, -1, -1, -1, -1, and +2. We do get a total charge of -2. That does make sense, but with formal charges, we want them to be as close to 0 as possible for the atoms. So let's see if we might be able to do another Lewis structure that has more zeros for the formal charges. When I see this +2 charge here on the sulfur, I know that I can move electrons from the outer valence electrons of the oxygen into the middle. So
we're allowed to move it from the oxygen to the sulfur because sulfur is in period 3, and it's so if we're in period 3 or greater, if our central atom is, they are allowed to have more than the octet rule satisfies. They can have more bonds, more than 8 electrons. So we can move these charges around, trying to get more zeros.
If I do that twice, if I move these 2 into the middle to form double bonds and get rid of them, I think that'll get rid of the +2 charge. So let's try that and then recalculate our formal charges. So I've moved electrons.
So now analyzing it, we have sulfur again is starting valence is 6. There is no lone pairs, no non-bonded valence electrons, 0. And we now have 12 electrons around it, and 6 bonds. 12 divided by 2 is 6. So using the equation, this has a formal charge of 0, which is what we like. Things do not like to have charges. We can look at these 2 oxygens here. They have 6 bonded and 1 pair. That gives us a -1. So these 2 have -1 charges. And these 2, they have 4 electrons. They started out with 6. And there are now 2 bonds between them. So 2 bonds, 4 lone pair, 4 non-bonded. It's not lone pairs, I keep saying lone pairs. 4 non-bonded valence electrons. That gives these a charge of 0.
From the outside of these 2 green oxygens into the middle to form double bond. Let's see how that changes the formal 12 total bonding electrons. So the formal charge on the 4 of the non-bonding, that works well with this.
So it still totally adds to -2 charge, but now we have way more zeros in this. This is a better Lewis dot structure for sulfate. And that's what it turns out to be. You don't have to worry about this. I don't teach formal charge. I should. But for the most part, leaving it off will get you the most correct answer most of the time. So, one more time. First one is Lewis dot. And the next one is geometry. And I found two tables for geometry that is better. This one. I think this one's better. It's just not harder to see. So this one I like the better. So if you only have two things coming off of the central atom, these things could be either atoms bonded or lone pairs. It's always going to be linear. If we have three things, then the electron geometry is trigonal planar regardless. If these three things are atoms, then the molecular shape, the molecular geometry, is trigonal pyramidal. If one of them happens to be an electron pair, then it's bent. If we have four things, then the electron geometry is always going to be tetrahedral. If they're all four atoms, it's tetrahedral. If one of them is a trigonal, or if one of them is a lone pair, that's trigonal pyramidal. And such. So for this homework, the underlined thing is the central atom. So carbon is always the central atom. And we have one of them, so they're all going to connect to the central atom. These are ions. Remember, a plus charge tells you that you're going to remove an electron. The negative charges tell you how many electrons you're going to add. Here we have some shape approximation too. You don't have to determine bond angles. I don't teach bond angles. You can remove part 3 off of that. Part of it cut off into the next page. Then the last part here is determining polar versus nonpolar. For this one, this is bonding electron pairs. Let's do the first, or let me choose one. We'll do a random one together. So let's look at number 5. Or no, let's look at number 6.
Mr. West, is Lucas Lakey in there?
He is.
Coach Boyle wanted me to send him to the gym for a little bit. She needs to see him, if that's
All right.
okay.
So bonded electron pairs is basically the number of atoms. So an X represents an atom that's bonded to it. So on this one we have 3 bonded atoms. By the way, this symbol right here. So so we have the central atom A, an electron pair here, an atom here, and we have this wedge with an atom here, and then we have these dashed lines here, X. What do you think this wedge, this line, and this dashed line mean? Do y'all remember what this looks like? It looks like a tetrahedral. But this is in 3 dimensions. This wedge means it's coming towards you. Out of paper. This dashed line means going away from you. It doesn't really matter. So going into paper. So into paper. It's just a way to try to draw 3D. So number 6, we have 3 bonded pairs. We have 1 lone pair. Add these together, we have 4 in total. So what is the electron geometry? So having 4 regions in total, then 3 bonded pairs and 1 lone pair tells us it's trigonal bipyramidal. Is the shape. Another thing you could do is, so we have 4 total regions. So we know it's going to be here. It looks like this. But one of them is a lone pair. So it's trigonal pyramidal. It looks like this. An example of this would be pH4. I think last year, pH3. I don't think you have to do examples or bond angles. You can cross out bond angles and examples. I should have y'all do it, but it'd be too hard for y'all to just sit there and guess until you get something. So phosphorus has 5. Phosphorus has 5. And then we have a hydrogen connected to it. So this is something that has an overall shape, an electron shape of tetrahedral, but a molecular shape of trigonal pyramidal. So it looks like this.
Mr. West, is Darby Diamond in there?
Here she is.
She needs to come to the office to leave, please, sir.
Alright. Does that make sense on the homework? If y'all can, do put an example, but I don't think I can take off if you don't. Only thing you missed was me explaining this. The dashed line, because it's in 3 dimensions, the dashed line, the wedge, the solid wedge, it means coming towards you out of the page. And the dashed line means it's going away from you.
So it's still a bonded pair?
Yeah. It's just trying to draw 3D. So, next week, we're doing benchmark testing. I will be reading a test out Monday and Thursday. Will y'all be doing benchmarks?
I don't know.
So Tuesday, I'm probably going to review, and Wednesday we'll have a test. So try to have the homework by Tuesday. Or really, I'd like the homework by Monday, if you can pass it around so I can grade it and give it back to y'all.
What about the domain?
So it says it under it. So for number 6, we did it together. So the bonded pairs, that's how many atoms you have bonded, basically. There's 3. For the lone pairs, the E represents a lone pair. Read the description. There's 1. And then the electron domains is E plus X. So this is E, this is X. If you just add them together, there are 4 regions in total, or 4 domains. Basically, count how many X's you have, how many E's you have, and then just add E plus X together. Yeah, you definitely don't have to do bond angles because we don't get that advanced in high school. There is, if you're curious why bond angles is important, if you're going to go into the drug industry, pharmaceutical industry, you need to know how your receptors in the brain are shaped, because it's literally like a key. Some of the molecules in biology fit together in a certain way to a receptor, and that's what you're trying to target.